This network represents the ultimate goal of modern AI design: autonomous agents capable of navigating the sprawling, interconnected environments of the real web. Delivering on that goal requires an agent to successfully chain multi-step actions across more than 16,000 temporal, real-world APIs. This chart compares pass rates on exactly that task. You can see the closed-source model, ChatGPT, completing complex API calls, while the baseline open-source models, Vicuna and Alpaca, score exactly 0. General instruction tuning optimizes an LLM to predict the next word in a language task. It completely ignores the structural logic required for tool use. Bridging this gap requires an architecture that explicitly targets the tool use domain. This is the structural problem the ToolLLM framework was built to solve. The ToolLLM framework proves that a 7 billion parameter open-source model can match ChatGPT on real multi-tool API use. To pull this off, the authors co-designed 3 interlocking pieces: ToolBench for the data, ToolLLaMA for the model, and ToolEval as the judge. The mechanism connecting all 3 is a specialized reasoning engine called the DFSDT planner. Instead of relying on a rigid text prompt to guide the model, this planner gives the agent an algorithm to branch its decisions and backtrack when it makes a mistake. Matching proprietary models at this scale requires engineering a reasoning architecture that actively handles failure rather than relying on raw parameter count. Training an agent to use tools requires data. The immediate bottleneck ToolLLM faced was the lack of a real-world multi-tool dataset, leading to what we call the sparsity problem. If you randomly select a weather API and a financial API and ask a model to link them, you create an incoherent, useless training task. The tools share no logical relationship. To solve this, they crawled a database of 53,000 APIs, filtered them, and used hierarchical sampling to group them into 3 buckets: single tool, intra-category, and intra-collection. Forcing sampling within the same category creates API subsets with genuine semantic coupling. The authors fed these coherent subsets, along with a few seed examples, to ChatGPT, which synthetically generated roughly 200,000 instruction and API pairs. They then deployed the DFSDT planner over these pairs. The planner automatically navigated the web and annotated over 126,000 successful solution paths. The agent uses the exact same scaffolding to annotate its own training data as it will use later during live inference. Standard agents operate on zero-shot planners like React, which follow a simple loop: generate a thought, take an action, and observe the result. A React agent is strictly linear. It suffers from error propagation. Hitting a dead API endpoint permanently poisons the remaining context. This causes limited exploration. The agent commits to a single direction, hits a dead end, and cannot reverse course. Scaling up the parameter count or running the prompt 10 more times will not solve these structural flaws. In practice, linear agents collapse when asked to chain multiple steps across the fragile, unpredictable environment of real-world web APIs. A straight-line thought process cannot navigate a branching temporal environment. This decision tree is the DFSDT fix. If a branch looks promising, the model proceeds and deepens the search. Hitting a dead end triggers the abandon mechanic, dropping the poisoned context. It then expands a sibling action, resolving limited exploration. This algorithmic loop of either proceeding or abandoning and expanding gives the model an automated failure recovery system. This prompts a specific engineering question: why use depth-first search instead of exploring the entire frontier with a breadth-first search? Depth-first search allows for an early return. The agent stops exploring the moment it finds a single valid path, avoiding the massive cost of burning API calls on every possible option. By implementing DFSDT, the engineers elevated their model from a blind sequential guesser into a resilient algorithmic problem solver. Even with a flawless planner, fine-tuning faces a hard physical constraint. LLM context windows are small, and API JSON responses are massive and highly nested. To prevent the model from truncating mid-task, the engineers used positional interpolation to extend ToolLLaMA's context limit from 4,000 to 8,000 tokens. This created a new retrieval bottleneck. 16,000 APIs mathematically cannot fit into an 8,000 token prompt. They bypass this by deploying a BERT-based dense contrastive retriever. Traditional lexical matchers look for exact keywords, but the dense retriever surfaces APIs based on their semantic meaning. In a massive database, tool discovery is a semantic search problem. Neural retrieval is mandatory to get the right options into the planner's context window. This grouped bar chart tracks pass rates. DFSDT strictly beats React, with gains largest where React fails most, on complex multi-tool instructions. Here is the final output. The 7 billion parameter open-source ToolLLaMA running DFSDT matches its proprietary teacher, ChatGPT. During testing, the researchers discovered that using the neural retriever outperformed feeding the exact ground truth API list. The retriever actively found highly effective substitute tools the annotators had missed. Securing these metrics required solving a philosophical evaluation problem. How do you score a model when a single prompt has infinitely many valid solution paths? Previous models, like Gorilla, used rigid structural AST matching to verify outputs. ToolLLM abandons that. Instead, it relies on ToolEval, a ChatGPT judge, to score executability as a pass rate and pairwise preference as a win rate. When real-world environments drift and the ground truth is fluid, deterministic structural verification breaks down. Scalable semantic evaluation requires an LLM judge. These engineering gains are inseparable from their specific trade-offs. DFSDT's branching architecture costs significantly more in API calls and compute budget than a simple linear pass. The framework also carries a circular dependency. It relies on ChatGPT to generate the training data, and then uses ChatGPT as the final judge, which inherently invites stylistic bias. Because RapidAPI endpoints drift, update, and die every day, these benchmark pass rates are subjected to temporal decay. They are not frozen in time. The system functions by coordinating hierarchical data generation, the backtracking logic of the DFSDT planner, and the semantic evaluation of the LLM judge. Open-source models can achieve parity with proprietary systems on highly complex tasks, but doing so means looking past raw scale and explicitly co-designing the training data alongside the reasoning architecture.